So a measure that we left out of our last notes for 12.3 was something we call standard deviation. So in general, standard deviation tells us how close the mean is to our actual data. So we'll have a mean like an average from before, but standard deviation measures how close that mean is to a fit. So if the standard deviation, or the term for that we could also call sigma, so Greek letter sigma is used to represent it. If that standard deviation is large, it means the mean is not very reliable, but if it's small, it means our mean is more reliable and it's a better fit for our data set. So the formula for standard deviation, and again we call it standard deviation with that Greek sigma, is the square root of the summation of x minus x bar squared all over n. And again, that's a lot of stuff all at once. Looks complicated, but it's actually easy if we take it in steps, and this is also something we're not going to have to memorize. So if we're trying to take all of those parts and break it into steps, so just trying to find that formula, given our sample data set, looks like we have 1, 2, 3, 4, 5 numbers to find a standard deviation for. First step is we're going to find the mean, which we call x bar. So we read that as x bar. Again, mean is just finding the average. So like we've done before, we're going to take those 5 data members, add them together to find a sum. So I think those all add up to 75. Just like with our other averages, we divide that by 5 because there's 5 data items. And we come up with 15 for a mean of that set. Next step, again, so far we found part of this formula. We found x bar. Next step is we want to set up a table because we're going to use that to find our differences, x minus x bar, and also the square difference, x minus x bar squared. Because remember in the formula, we see x minus x bar, but we're also squaring it. So for that table, what we mean by setting up that table is we're going to take each data item, so 12.6 for example, we're going to subtract the average that we just found, so we found an average of 15. We're just going to keep track of that difference. So if I take the first number, subtract the average, we get negative 2.4. Second number in that set, subtract the average again, I get 0.1. So on and so forth, because again, we're just taking those 5 numbers, subtracting 15 every time. We just want to see what the difference is between the actual data value and the average that we just found. But remember, in the actual formula, we have to square it. So in the right-hand side of this table, taking the number that we first found, we're just taking that and squaring it. Notice that it doesn't matter if your first number was negative or positive. Anytime I'm squaring that difference, it's always going to come out as a positive value. So negative 2.4 squared, for example, is a positive 5.76. Positive 0.1 squared, again, is still a positive 0.01. So that's what we're doing. We're taking those differences from the first column, we're squaring them, and just keeping track of that result as well. So on the right-hand side, after we're all done with that table, we should have these squared differences between the data values and that mean. So next what we're going to do in the actual formula, we see that capital sigma means we're just going to sum all of those together. So that x minus x bar, the category you saw on the right-hand side of that table, going to add up the right-hand column, and that's going to be our new sum. So if I take 5.76, that was our first row, add all those together, so plus 0.01, plus 14.44, 8.41, 10.24. Taking all those numbers for the right-hand side, add them together, should come up with 38.86. And then the only thing we have to do is substitute that into our formula. And again, 38.86 in our formula was the numerator in that fraction. So if I want to take the sum divided by n, that's the part that goes inside my square root in the formula. So what we just found from that table, once I've added up that right-hand side, got 38.86. Since there are 5 data items, I take that, divide it by 5. And then once I have that division done, I'm going to finish by taking a square root. If I take a square root of that fraction, or sorry, decimal, it comes out to about 7.8 or so. Taking a square root is going to give us about 2.79. We're going to use that rounded number as our answer for, again, this would be our standard deviation. So again, it's just going to be 4 steps every time, walking through those steps really briefly. Take an average first, just like from our earlier section. After we know the average, we're going to find those differences and square those differences. Add those up also, divide by the number of data items, take a square root, and that's our standard deviation. So let's try that again with another set. Again, there's a few steps to it, but it is the same steps every time. First step, again, if I'm given the second data set, is I'm going to start with an average, add all those data items together, and divide by 5, because there are 5 items in that set, so 5 elements, and that gives us 14.5 for an average. Next part is we're going to fill out our same table as before. So we're going to take our data value, subtract the average, and come up with a difference. So again, we're just taking each of those numbers, 13.4, subtract the average that we found, and we're going to come up with a difference for each of those 5 data items. Next, remember we have to square those, so whatever we just got on the left-hand side, going to take that number and square it. And remember, just like from before, we should see that all the numbers on the right-hand side of the table are positive, because even if I take a negative and square it, it's going to come out as a positive value. So once I filled out that table by finding the differences and then squaring them for the right-hand side, I'm going to take all those right-hand values and add them together. Because again, that summation in the formula means we're going to add all the right-hand side together. So if I add those 5 numbers together, 1.96, 784, 1444, 0.09, and 0.04, adding together the right side of that table should give us 24.37. So trying that again with the last step, I got to take that sum that I just found, 24.37, divide that by 5 because we have 5 data values, and we get 4.874. Finish by taking the square root of that, and we should get about 2.21 as our standard deviation. So again, same steps as before. Find an average, find the differences between that and each number, square those differences before adding them together, plugging them into my formula, and then we're just trying to take that square root to finish. So same 4 steps every time, although it does take a little bit of work if we're doing standard deviation by hand. One question I answer on the bottom is which data set would have the what we call better standard deviation. And again, better in this case means we're looking for, going back up to our description, looking for a small standard deviation. If we find a small standard deviation, that means our mean is closer to our actual data numbers. So in this case, if we're looking between those two, it looks like the first set, 2.79 was our standard deviation. Second data set had 2.21. So in that case, our second data set is the better standard deviation because, again, a smaller standard deviation means the mean is a more reliable estimate of most of those data members. We see that most of the data is closer to our average than it was in the first set. So again, smaller standard deviation is what we're looking for if we're looking for a better estimate with that mean. So we could see this as well in what we call, this would be something you see in stats as well, something we call a normal distribution. But standard deviations, again, can be represented by this curve, where the curve is spread out, the data is spread out from the mean and is less reliable. So if the curve is close to the mean, the data is more reliable. In this case, close to the mean means centered towards the mean in the middle. Notice we kind of put the mean in the center, and we go further out, so adding standard deviations to the right or subtracting standard deviations to the left. And the closer we are to the mean, again, the better fit our data is going to be. So our spread out standard deviation would look something like this. Notice in the first example, we have kind of a taller graph that's centered towards the middle. Still have a center in the middle, but if I have a bigger standard deviation, we're going to have a little bit more room in the tails. So off to the left and the right, there'll be a little bit more space. And also the middle, I wouldn't reach as high. So it'd be a little bit more spread out distribution if my standard deviation was also spread out. So other than standard deviation, we're also talking a little bit about residuals, and this goes along with what we're doing with our trend lines from earlier. So a little bit of a description there. I'll just kind of summarize. We can always read back through it later. But the idea here is that we're going to look and see how close our estimates of our trend lines, how good those were to fit with our data. So what we mean by residual, because we have residual values, we're going to be using residual plots, is we're looking for the difference between the y value of a data point, so what we actually see in our set, and the corresponding y value of our model for the data set. So basically it's measuring how close is our actual value. So in this example, like our actual data point on our scatter plot would be up here. How close is that to what we would predict on that trend line? So I try to fit my trend line to our data. We've seen that a lot of times your points end up above the line or below the line. We're trying to find about how close they are for each one. So we could have a positive residual if your data ends up above our prediction. Could also have a negative residual if our data ends up below our predicted value. And again, what we're going to be finding is y minus y hat. So we call that symbol y with that little marking over it, y hat. Represents the value of the data set. So y is our actual value, and y hat's going to be what we predicted for that value using our trend line. So try to do that with this table as well. So this is giving us some heights for certain ages. If I treat my age as my x's and my height as my y's, we'd be able to make a scatter plot. But let's just say for our trend line, we came up with this equation, 2.3x plus 33.4. The idea of finding y hat is we're just substituting our values to make some predictions. So for example, for a 5-year-old boy from 5 to 13, I would plug in 5 into that function, and that's going to give me a prediction for a y value. So take 5, substitute it into my trendline equation. That would predict that a height of a 5-year-old boy would be 44.9 inches. Same thing to fill out our table. Could substitute 6 into our equation. That's going to give us 47.2. Substitute 7, we get 49.5. And we're going to fill out our table just by doing that each time. We're just going to take our x and plug that in, seeing what we get back as a y value. If I substitute in 12, for example, 12 times 2.3 plus 33.4 should end up with 61 as a prediction. So we fill out that table by making our predictions, and then on the next page here, we're going to find that difference, kind of like what we found from before with our standard deviation. So again, y minus y hat is comparing what's our actual data value for y, and how does that compare to our prediction for y hat. So going back up for our first example, if I'm looking at a 5-year-old boy, the actual value from our table is that they were 44.5 inches. Our prediction from our equation gave us 44.9 inches. So we just got to find that difference for each age. Take our actual value, subtract the prediction, and that gives you a negative residual of negative 0.4. If I try that again for age 6, for example, the actual height was 46.9. Our prediction was 47.2. So if I subtract those two, 46.9 minus 47.2, we have another negative residual. So I filled out the rest of the table that way, took my actual height, subtracted what height we predicted. That's going to give us a residual for each box. So we get a few positive residuals where our actual value is a little bit higher than our prediction. Also have a few negative residuals where our actual height is a little bit lower than what we predicted it to be. But either way, we're going to fill that out the same way every time. Take your actual value, subtract your predicted value. That's going to come up with that residual plot. So for our residual plot, we're going to take the points. So x is still age. And again, y minus y hat, that's the table we just filled out at the top. That's going to be what we're plotting as a y value. So what we're looking for now, if there's a pattern in our residual plot that we make, the best fit line is not going to be a good representation of the data because it means we made some kind of consistent error. If there's not a pattern, the best fit line is a good representation, just because we have no clear pattern, no kind of clear mistakes that we're making. So again, this would be an example where I have a best fit line that would be a good prediction. But this, since I'm making a sort of U-shape or a parabola shape, this would not be a good fit for our data if I could see a consistent or clear pattern. So again, what we're doing is we're taking x, which would be age, and y minus y hat is our residual. So our first point, for example, would be 5 and negative 0.4. Another point we would graph out at 6 and negative 0.3, 7 and 0.2, 8 and 0.4, and so on. And I plotted those out right beneath here. So again, ages were going from 5 to 13. We had some positive residuals, we had some negative residuals, and I put these into a residual plot. And again, should match up to what we had the table at the top. So for example, if I look at 12 as an x, negative 0.1 should be the y value. So I have that on my graph as 12 and negative 0.1. This would be our residual plot, and one last question to answer here, which is the best fit line a good fit for the data? So again, the goal here is we want to look to that residual plot. If it looks random, that means we'll have a pretty good fit for our trend line. And it looks like it is pretty random, so I'd say yes. There's no clear pattern in our residual plot. I don't have a U shape. I don't have a consistent line shape. If I just have, looks like kind of a random collection of points, this is going to be a pretty good fit for my trend line. So again, just make sure you have these notes completed. We'll work on that corresponding practice in class.